In the last segment, we talked about gas law stoichiometry. And again, you should have been watching or have watched some YouTube videos that I put on Blackboard for you with some other examples. You tried the ones in your lecture notes that you compare now with the answers that I've shown you. And you should, as always, be trying problems in your book. Segment 2 now begins on page 7 in your lecture notes, which is Dalton's law of partial pressures. And this is new for some of you. Dalton's law of partial pressures says that the sum of the individual pressures equal the total pressure of the system. And this is useful in a number of situations, one of which is when you collect a gas over water. Because when you collect a gas, you can't just collect it. You usually have to collect it over water so you can calculate the volume. And we should do that in the lab. Okay, we don't do it every single semester, but we should have that experience in the lab, and it's best left to that situation. I do have a couple of problems here, though, on Dalton's law of partial pressures, which you can see in your lecture notes. One is the planet X, where we have nitrogen and oxygen, and so there's a calculation there. And then as a semi-tangential aside, but not entirely, don't ever breathe in dry ice because you'll probably suffocate. Actually, if you want to euthanize rodents in biology or physiology lab or some such thing, you can suffocate them with dry ice. Not very pleasant. All right. Everything up till this point is what we would call an ideal gas. Ideal gases are ideal because the distance between particle A and particle B is basically infinite, and particle A, particle B leave each other alone, and therefore we have all those gas laws. P1V1 equals P2V2, V1 over T1 equals V2 over T2, etc., etc. When you take particles and you smush them closer together under high pressure or low volume, then the gases become non-ideal. And that is a perfect segue into what happens when you push those particles together and you create a liquid. So at this point, what you need to make sure that you're doing is that you are working on gas law problems according to whatever instructions that were given to you on Blackboard or in the classroom regarding video problems, lecture note problems, or practice problems for a practice exam, or in-class problems. That then brings us to the liquid state, and this is new for many of you and not particularly well represented in your book. But the fundamental thing that has to be true in going from the gaseous state to the liquid state is that the particles that are infinitely far apart have to be smushed closer together, and they have to stay there. If they don't stay there, they can't become a liquid. Okay? And so there are some things that pertain to liquids that don't pertain to gases. And that is compressibility. You can't really compress this, okay, because those are already smushed together. Viscosity means resistance to flow, and so usually liquids are viscous. Surface tension means the tension at the surface. Okay, and so many liquids will have a surface tension because the particles are being held together. Now, kinetic molecular theory says that molecules move. And so that means that liquids will exhibit something called vapor pressure. Okay, so if I have, say, some water, all right, so water is going to look like this. And you should recall from Vesper theory that water is going to be bent, and you should also recall that it's going to be polar. Okay, so here's your water. And because they're smushed closer together, there has to be something that's going to attract them. Okay, so indeed, the partial negatives are going to be attracted to the partial positive neighbor. Okay, so these are going to attract, and that is going to be what keeps these together in the liquid form. All right, now molecules move according to kinetic molecular theory. So these water molecules, you could think of them as moving around, moving around, moving around, moving around. Sometimes the particles move too fast and they escape from the liquid phase into the vapor phase. Okay? And the propensity to do that is called vapor pressure. Okay? So what variables would increase vapor pressure? Well, it's usually temperature, because as we increase temperature, we increase molecular motion. As temperature increases, what happens to vapor pressure? It increases. When the vapor pressure of the liquid is equal to the atmospheric pressure on that liquid, then we have reached the boiling point. Okay? So when we go from liquid to gas, that's called evaporation. Gas back to liquid, that's called condensation. Okay? And specifically, when the vapor pressure of the liquid is equal to the atmospheric pressure on that liquid, we call that the boiling point. Now, you notice the double arrow. Okay, so if I come back here, liquid to gas, gas to liquid, okay, the double arrow means that this is reversible. And that means we're going to call this equilibrium. Okay? Now we're going to come back to the business of equilibrium in the next unit, because that is very important to moving forward. Okay? Now again, one of the things that we're interested in is what keeps these molecules attracted. What's going to keep them attracted? Okay, so what I alluded to over here was the partial negative, partial positive attraction between these neighbors. And indeed, that is one of them. Okay, so we want to go back to this business of polarity, and to be sure that we can determine a polar bond when we see it. Okay, so again, water. Here's our Lewis structure, Vesper. Okay, so I'm going to say Lewis and Vesper. If you don't remember what these are, you need to go back and review them. Okay. Ammonia, lone pair, so this is going to be a pyramid. CH4 will be a tetrahedron. You can draw it like this if you wish. If you don't like that, you can just draw it like that. Makes no difference to me. This one, carbon is king. You link them together. But you'll have lone pairs on your oxygen, so it will be bent. 1, 2, 3, 4. Hydrogen, 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 hydrogen. Okay, so those are your Lewis structures. And then as far as polarity, remember where you go look. Where do you go look? You look at an electronegativity chart. Okay, so partial negative, partial positive, negative, plus, 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 negative, plus, and this has no polarity. Okay, so if you don't remember how to determine whether a bond is polar or not, you need to be sure to go back and review that.